As Leah said, it's about the PSI's energy system integration platform, which is a demonstrator. And I would like to introduce you to the topic of energy storage using this analogy of human power systems. You see on the left-hand side sprinters that can run in less than 10 seconds, 100 meters. And on the right-hand side, we see marathon runners who can run the marathon distance in 2 hours. And that translates to 17 seconds for 100 meters. And then there's the question, why is there a difference actually? Why can the sprinters not keep up the pace to run a marathon distance? And well, the answer is they rely mainly on glucose. So they are high power system basically. And the marathon runners, they are more like a sustainable power system. They use glucose and fat, and this fat serves basically as an additional energy storage source that these runners can access, and they cannot access it. So it's about the energy storage they have, it's about energy conversion. They can access the different energy sources differently, and they have conditioned themselves to be able to do that. And that's what we most likely will have to do in the future with our electrical power system or the entire energy system. We see here a graph about some electricity balances of Switzerland. On the top left, we have the net between power production and consumption. So in the last couple of decades, we basically generated more power than we consumed, and we were able to export this power then to neighboring countries. However, in the last couple of years, from 25 on, 26 on, we had net import during winter periods. And knowing this, and also knowing that we will have the electrification in the future's power system or energy system of the mobility, which will lead to additional load on the electricity grid and also employing heat pumps, and possibly the phase out of the nuclear power generation will also affect the electrical power system. Further on, then we have most likely an increase in population, further electricity demand, and there will be maybe restrictions with the net traffic transfer capacities of electricity that we can import to our electrical power system. On top of that, there might be weather effects like the Dunkelflaute, and basically where no renewable energy can be harvested, and that might lead in future, that's a hypothetical scenario I've sketched up here, that we will have the possibility to import around 10 terawatt hours of electricity, but we will still have demand that is not satisfied. And that's why we need something like in the runners scenario, an additional energy source, for example, hydrogen or methane, that we then can access and reconvert back to electricity. And that's one use case, seasonal energy storage, that the platform can provide data for, but also for other applications. I will cover one later on in the talk. So the demonstrated energy system integration platform is about renewable energy storage. And to store renewable energy, you need to be able to convert the electrical energy to another vector and back to electricity. So that's what we want to investigate, the characteristics of the different chains comprised by the power to gas to power path. We also want to demonstrate this energy storage using relevant technology readiness levels. So the power plants we have, you will see that later on in the features, have a nominal power of around 100 kilowatt. And we want to build a bridge. I mean, it's nice that we have this small bridge here from the ESI platform to the areal of PSI, but this could also be the outside world, like the industry and the public sector, where we want to have the transfer of the technologies to the industry, for example. And it can be also used as an educational platform to transfer the know-how to students or other scientists. What I'm going to cover today is basically the purpose we just saw. It's about energy storage, energy conversion, that we want to demonstrate with this ESI platform. Next, we will talk about the features of it, and then how the features contribute to specific case studies, where we investigated what possibilities are there to use the platform. And last but not least, of course, the application in Pathfinder. With respect to the features of the energy system integration platform, we see here a sketch diagram, which shows us on top the renewable power generation that then can be stored using the hydrogen path in the middle. We have an electrolyzer, gas cleaner, storage tanks, and the fuel cell. And on the bottom part, we have the methanation taking place. We have two containers, one for dry and one for wet biomass. So we use the CO2 stemming from biomass, or one also could use the CO2 from the industry to form with hydrogen methane, which then will be fed to the gas grid. And we will focus in this talk on the energy system integration platform's hydrogen path. The hydrogen path, as I said, consists of electrolyzer. In the electrolyzer, we have stacks that have cells with polymer electrolyte membrane cells, so it's PEM-based, and also the fuel cell container, the stacks built in there are PEM-based. The entire chain also uses, next to the hydrogen, which is stored in this tank, oxygen. So we have two large tanks and a small tank for the methanation where the CO2 is stored, such that they can do their tests. So it's based on pure oxygen instead of air. The gas quality we can store is 4.5, so it's very clean. No impurities are basically in there, and it's also very dry. We achieve a dew point smaller than -60 degrees C. And the platform in itself allows for intermittent operation, which is required for the storage of renewable energy. It's connected to the low voltage grid, and it is fully automated. That means we can access and do case studies using the power plants, electrolyzer, and fuel cell from remote places. The data acquisition system comes with a sampling time of 5 seconds and is based on a Siemens process historian system. I would also like to highlight that the demonstrator is also technology oriented, and we see that in the build-up phase diagram here. In 2014, we started it. We wanted to build this platform. So people thought how to do that. We bought an electrolyzer, installed it, and the tanks were installed. We see that in this small video. And we then went on in collaboration with Swiss Hydrogen to build the fuel cell systems, 50 kilowatt fuel cell system, and integrated it in a fuel cell container. And the last point of the fuel cell container was in 2019, where we achieved to operate 100 kilowatt of fuel cell power to be fed into the grid via a series connection of fuel cell systems. Next to that, we have features like testing infrastructure for other fuel cell systems, which will be used also for Pathfinder later on when we want to test hydrogen air systems. And we improved already some parts of the processes, like the gas cleaner, which allows now us to start up the plants or the power to gas, power to hydrogen path much faster than before. And last year we did some remap tests, and one of the results I will show you now in the case study slides that follow now. The case studies, the first one is about electrochemical energy storage. So not only seasonal energy storage, as I already mentioned, is a possibility to use hydrogen and the conversion processes taking place for this energy storage, but also, for example, peak shaving a fast charging station at the highway rest stop. We see that on the left-hand side, we have a Porsche Taycan, which has a charging curve. So that's in kilowatt power over the state of charge. We then translated this curve to power over time, and we were able to use MPAS eHub battery to basically simulate this charging behavior. And if you don't do anything, you will cause a relatively large stress So it was basically also scaled down to 100 kilowatt because the battery at EMFA was not able to further increase the power. You would cause large stress if you drive 100 kilowatt or the 270 kilowatt of power over a transformer. And if you can peak shave that, of course, that would be a nice thing. And we will see later on here that you can optimize the operational costs. And we demonstrated that it is feasible with a hydrogen energy storage system to peak shave such a charging demand. We see here the aggregated powers over the virtual transformer station, and that it actually pretty much follows the peak shave limit of 30 kilowatt. And by that, we also demonstrated that the ESI platform is accessible from the outside world and can be remotely controlled. On the right-hand side, we see then simulation results. And now it takes some time to understand that. We have the total cost in millions shown here on the y-axis, varying demand charges, which were used in simulation. That's the penalty you pay for the maximum peak per month. And we have different scenarios: battery energy storage system, hydrogen energy storage system, with the expensive costs of capital investments of today and the future assumed costs, which will be cheap. And we see in the red part that with increasing demand charge, the operational costs, of course, increase, and that with today's cost, we are actually not cost competitive when employing energy storage systems to peak shave demand profile that was used in this simulation. However, if you use the cheaper investment costs, we see that the operational costs in red surpass the green and the cyan areas, which means that basically energy storage systems will be profitable to be employed in such cases. The second use case I will talk about is the advanced control algorithms for the future energy system. It's about electrolyzer, or was about electrolyzer modeling and real-time control for optimized production of hydrogen gas. We see of the Silyzer 100, its representation sketched here. So there are different parts within the PEM electrolyzer. We have the power converter stage, basically rectifiers. We have the stacks. We have pumps, several pumps to achieve the cooling of the stacks. We have external coolant loops and passive elements within the electrolyzer. And if you want to use an electrolyzer in model predictive control, you need to derive a suitable electrolyzer model. And we did that using system identification. So we now have a tool that also can be used for the fuel cell. We can do similar steps to derive a fuel cell model later on. And the test for the model predictive controller was the setting of having a refill demand of fuel cell cars. It's given here in kilowatt hours. We have on side of that boundary conditions that we can make use of renewable PV generation. And we had a varying price for the electricity drawn from the grid. The performance of the model predictive control is shown here. I mean, the mixed integer linear problem formulation made use of a more accurate model out of this diagram I presented here, and the linear problem formulation was a bit more inaccurate. And we see that now, when we know that the electrolyzer actually has the best performance at 100 kilowatts, so it's there where it is most efficient, that if the power drawn is not at that level, it's less efficient. And we see that's here the case, that the LP is drawing power from the grid at like 80 kilowatts, but the mixed integer linear problem formulation is running at 100 kilowatts. And so we unnecessarily fill the tank storages to higher levels with the LP. And therefore we can conclude that the mixed integer linear problem formulation was performing better. And we could use, therefore, the platform to validate control algorithms. So that's the second case study. The third case study, and that's the last one, is about power system frequency control using the PAN technologies. So if you have disturbance events in the synchronous grid of Europe, these are shown, there's an example shown here, data result existing from 1997. We see that there were several disturbance events before that year, which were then mapped on this graph, and they amount to 1 gigawatt to 3 gigawatt. And so one needs to have about 3 gigawatt of reserve power for primary reserve control at hand to counterbalance such disturbance events. And if you want to participate in this primary frequency control reserve market, you need to be able to perform tests that validate your technology to be suitable for such tasks. And we see here the results for primary frequency control tests. We also did for secondary frequency control tests, some tests which also were successfully carried out. In the primary frequency controls case, we see that the frequency can increase from 50 to 50.2 hertz, or decrease from 50 to 49.8 hertz. And then the power plants must react correspondingly. In the case of the electrolyzer, we see here in the green curve the response, and in blue we see the response from the fuel cell. And the same is true for the right-hand side plot, again the fuel cell, and here the electrolyzer performance. And we see that these responses always stay within the dashed lines. This means that the tests were successfully carried out. Next, to determining the suitability, which was demonstrated successfully, of course, now, we determined the maximum ramping dynamics we can achieve with the PAN technologies, and we also determined the efficiencies, which I will show you on the next slide. This was done in collaboration with Swissgrid, again, using this relevant technology level we have with the demonstrator. The slide shown here is about the efficiencies, as mentioned. The top of the slide is about the performance of the demonstrator platform. We have technology readiness level 5 for the fuel cell and 7 for the electrolyzer. I mean, the electrolyzer was built in 2011, but the test data is from 2019. And so we see if we feed 100% of AC power to the chain, to hydrogen to power chain, we can re-electrify only 24.5%. And now you may ask, why is that the case? And for that purpose, in the work we derived what are the different losses making this large decrease of total loss. We have the balance of plant, we have the converter stage, we have electrochemical losses, we have gas crossover losses in the electrolyzer case, and we do have gas utilization losses in the fuel cells case. And if one sums these values up, we see that amounts to 52.9%, which is also displayed here. And then you can take measurements from the laboratory or from data sheets and say the performance in 2040 is most likely this here shown. And so we can calculate the difference and then derive the performance in 2040 overall. And overall seen, we will feed again to 100% of electric power to the electrolyzer, and then we should get out 48%. So using the demonstrator, we have now fundamental efficiency data available, which can be used for scaling the technologies, either up if desired for larger districts or down depending on the use case. We have a base for techno-economic analysis, and we have done that using pure oxygen. So with respect, and again, highlighting that we used pure oxygen, we also would like to do similar studies using hydrogen air systems as shown here. And we also want to determine the dynamics and efficiencies in a more detailed manner. We want to include the degradation data and then provide control-oriented and high-fidelity models to work package 2. And there is already close interaction going on with Work Package 2, and maybe there will be further collaborations then between Work Package 6 and 1, either directly or I would say probably more indirectly over Work Package 2. So then we also want to have these models in a relevant scale scaled up and provide that to the Work Package 2. And we want also to do an assessment on salt caverns that can be used for large-scale hydrogen energy storage. And last but not least, for this slide, I would say, since our demonstrator is now accessible over Remap, there might be other case studies that are of interest, like heat-coupled hydrogen energy storage systems. So if you would like to do that, please contact us. We are looking forward to carry out such tasks. And how can we do that in the end then is by using the user interface. I mean, you could come to PSI and just use the human machine interface of the corresponding power plant. Here is the fuel cell shown. With that, we would have a lot of flexibility implementing different control strategies already on the low level side, but there is also then risk coming with that. And if we go to the high level control scheme, there is less risk, but also less flexibility. Nonetheless, you can then remotely access the demonstrators. And using the high level control, the supervisory computing data control and data acquisition system that is being connected to the REST API using OPC UI from the Venus Energy platform. You can then develop using Python, MATLAB, or Labio code your control code for your use case, and then you can control the power plants locally at PSI. To do that, you need a user account. You can get that from the project leader at PSI or ETH. Once you have a user account, you can access the wiki and example code and perform your source code down here. With respect to the limitations, as in EMPA's case, we do not have a simulation environment. We do not have a battery here, but EMPA does, of course, and we do not have a standalone microgrid nor a smart grid, at least not yet. Maybe in a future extension phase, we will see, but EPFL does have one. So we complement each other quite nicely. And the users we expect or have had so far were researchers that did control algorithm development or system analysis, and industry partners who developed components or did system development on the ESI platform. For future collaborations, of course, it would be interesting to have collaboration between distribution system operators, electric utility companies, and we would also like to test further fuel cell systems from heavy duty or car manufacturers. Also, possibility would be to work with aerospace companies because they also intend to employ fuel cell systems in future airplanes. With that, I come to the end of my lunch talk. We want to thank, of course, all the contributors to the energy system integration platform Demonstrator and all the people who contributed to it. And if you have also questions later on after the 15-minute session that follows now, you can contact me or Felix Büchi. Thanks for your attention, and I'm open for your questions.